What is this? Yeah. You're making proud here.
All right, so we'll have the final session of the symposium, and we'll start it off with Jane Kim at OU, and she'll talk about variational methods with neural networks.
Thank you very much. So I intentionally kept my title a little vague. I didn't know totally what I was going to talk about. So I will focus first on neural quantum states, variational Monte Carlo. At the end, I'll try to talk about some ideas for the future, but they're very rough, so take everything with a grain of salt. Oh, yes. All right, so let's start by talking about variational Monte Carlo. Now, this is one of the simplest, no, it's not the simplest method in the quantum Monte Carlo family. It's just a collection of quantum many-body methods that use Monte Carlo integration to approximate very high-dimensional methods. So the basic idea is to take some trial wave functions. This is going to be designed specifically, usually for a Hamiltonian that you are looking at. And it's going to bake in all the symmetries, boundary conditions, and preconceived notions of your wave function. And you update the variational parameters so that you minimize the expectation value of the energy here. So I won't go into detail about the specifics of Monte Carlo integration, but that's the Monte Carlo part here. So, variational Monte Carlo, again, is the simplest method in the family. So usually it's used as a first step before more sophisticated methods. The one thing that I'll mention later on is diffusion Monte Carlo that we use as benchmark, but some other very popular ones, Green's function Monte Carlo, auxiliary field quantum Monte Carlo, et cetera, et cetera. There's a huge diverse set of different methods. So the basic idea is as follows. You sample a bunch of configurations from your wave function squared. Then you use those samples to compute the ground state or the expectation value of the energy as well as the gradient with respect to parameters. Then you update those parameters in some way. So we talked a little bit about optimization methods like Atom. Yeah, you can use that, but we actually don't. So I'll discuss that in a minute. Now, when we introduce neural networks into the mix, we are basically trying to find a very, very flexible parameterization for the wave function. And the first time this was done was only in 2017. That's not that long ago. So this field is quite new. And since then, it has really exploded. So it was first applied with restricted Boltzmann machines to spin systems. And now we're on to nuclei, and there's lots of people in quantum chemistry that's working on huge problems. But the variational Monte Carlo part is basically exactly the same. So the goal is to create a very flexible neural quantum state. And the general philosophy that we have is that we want this neural quantum state to be as small as possible. Yesterday, we talked about these large language models, how they have millions and millions of parameters. The downside of that is that nobody else other than Google can really replicate that. We'd like to be able to share what we learn with these neural quantum states with everyone else. So we'd like this to be as small as possible. But still, even as small as they can be, it still requires many more parameters than traditional variation Monte Carlo. So for example, traditional VMC, maybe you need 10 to 100 at most variational parameters. We typically work around 10,000. That's still very small compared to millions or tens. And here's just a little cartoon of the same algorithm that I showed on the previous slide. It's just put into a more machine learning context. So this is kind of the cyclic cycle for reinforcement learning, where in our case, our agent is a trial wave function. And the action that we take, the interaction between the agent and the environment is this Monte Carlo sampling. So this agent traverses through Hilbert space, picks up a bunch of different samples, and from its experience can then calculate the cost or reward. So in our case, it's the energy, and then update the state by calculating the gradient, updating it in the usual way. Now, I mentioned that our wave functions are pretty large, but they're small in the context of neural networks. So this means that we can use a more sophisticated optimization algorithm, which is second order, and it's based on imaginary time propagation, but it's really closely related to the natural gradient method. And so that's more of a machine learning context, so you can derive it in a completely physics way by applying the imaginary time propagator for a small step in imaginary time on your initial state, and then trying to find the changing parameters that best fits that small step in imaginary time. And so you do some math, and you end up with this linear equation. On the left-hand side is that difference of parameters that we're looking for. And on the left, acting on this vector is this so-called quantum Fisher information. Now, this is a tensor that kind of describes, the difference between two states in Hilbert space, because it's not a Euclidean distance, because they're probability distribution. So this, when we invert this and solve for delta theta, this is kind of like preconditioning the gradient here. So we're not only looking at the gradient, but also a little bit of the curvature. So this improves training significantly, and it makes it possible for us to compete with these very, very large neural networks that have millions and millions of parameters, because ours, we optimize in a better way, but we only have about 10,000. So some recent news is that our paper on ultra-cold Fermi gases was published just a couple of weeks ago. So I will try not to spend too much time on this, because you can read the paper for yourself if you really want to. We also have a more casual behind the paper blog about this paper in general and some of the struggles that we encountered. And so if you are new to neural quantum states, I recommend looking at this blog first before jumping into this paper. Now, I'll talk a little bit about our system. If you haven't heard about these ultra-cold Fermi gases before, they're very strongly paired systems. So in our case, we're using them as a test bed for developing an ansatz that handles pairing correlations very well. And we're focusing around the unitary limit. You can read more in the paper, but there are just two main points. We have this Lovato, which is a different way of constraining the antisymmetry. It's typically not used. And then we have a message passing on. So those are the two main things I want to focus on. The motivation and everything you can read for yourself. Now, first, with the Lovato, it's the simplest and most general way that you can build an antisymmetrized product of pairing orbitals rather than single particle. So, in a regular Slater determinant, we have an n by n matrix, n different single particle states, n different single particle degrees of freedom. You plug everything in, fill in this matrix, you take the determinant, and that automatically is antisymmetrized. This is similar in that we still have an n by n matrix, but we discussed how to deal with odd n, but let's just assume that n is even right now. And this matrix needs to be skew symmetric and even dimensional. And so if you plug in all of the different pair degrees of freedom into this pairing orbital, and this pairing orbital is antisymmetric, then applying this Lovato onto this matrix is going to constrain the antisymmetry of your fermionic wave function in the same way that a determinant would if you're working with two particle. And so if you want to read more about the Lovato, you can check out this very nice paper. In this paper, they decompose explicitly this pairing orbital into singlet and triplet contributions. And basically like splits up into different blocks where the singlet and triplet contributions are all separate. But here we're not doing any of that. These inputs, these xi's and xj's, include both the spin and the positions. If we were working with nucleons, we could just add in isospin. And so we take advantage of the universal approximation theorem by parametrizing our pairing orbital using a neural network like this. And then, because these inputs include these spins and isospin degrees of freedom, this naturally encodes singlet, triplet, pairing, because we take anything as input. The second thing I want to focus on is this message passing neural network. This is a type of graph neural network. And so we encode this quantum system onto a graph, a fully connected graph, where each of the nodes represent each of the particles, and all the edges represent the relationships between. So this message passing neural network, we used a version of it for the homogeneous electron gas. The only difference here is that we also include attention. If you heard of that very famous paper, was it attention is all you need? So we include this here. But in this work, we use a simpler version without attention. We just increase the depth of our message passing. We also include skip connections. I'll show a little picture later what that looks like. And here's the setup. We have two different streams of information corresponding to one body and two body features. And so for the visible nodes, we include just the spins. We don't include the positions right here because we want to constrain translation convenience. And then for the edges, we include periodic versions of the distances, the separation vectors, and then the products of the spins. And then we do one very minor pre-processing step. This is mostly to get all of the hidden vectors to have the same dimension. This probably not necessary.
Sorry,
Yeah.
can you relate these R's and S to the X's from the previous slide? It was X just
Oh, yeah,
a
so
pair of
X-
R and S?
X is going to be R, so Xi would be Ri and Si.
SI.
Yeah, so this is kind of what we're going to use as our input for the 1 and 2 body streams. And then I have this picture here that makes it a little bit clearer. So we have 1 body stream here, 2 body stream here, and they exchange messages with one another so that it's mixing all of the information together. And this is done in a permutation equilibrium. So we start with spins, periodic distances, separation vectors, products of spins. We mix information together, and then notice that we have these skip connections. So whenever you see these dashed lines, this represents a concatenation operation. Basically, everything I'm talking about today can be done with the linear transformation, affine transformations, activation functions, pooling operations, and concatenation. I think that's pretty much everything that you'll need. So, in each layer of this message passing neural network, we pass this message, parameterized by neural network, then we use it to define new 1 and 2 body hidden variables. At the end, we concatenate everything together, and we end up with translationally invariant pairwise features that we then feed into the pyramid. So, okay, now I'm going to show you a little bit more detail what happens in each step. So on the left.
Oops,
So
sorry.
understood.
That's a reminder for me, sorry.
Oh, that's okay. On the left-hand side is a cartoon of a fully connected graph. On the right-hand side are the equations involved. So the first step is to construct the message. So let's say I am trying to update this edge right here. And I would take some information from the old edge as well as the node that's connected to it, and then pass everything through a feed-forward neural network. So now I have a message for each of the edges, and I do the same for all of the edges, all simultaneously. And then I use this message to update all of the hidden edges. So I do the same transformation over and over again and practice all simultaneously until all of the edges are updated. So notice the things that have been transformed have turned purple now. So now let's work on changing the nodes. And so the first thing we do is this pooling operation. So for each eye, I'm going to look at all of the neighbors and pool over the messages that are sent from those neighbors. So I update the hidden nodes in a very similar way. The only difference here is that this message that's for a given node is actually not parameterized in the same way. It's just a pooling over the existing edge messages. And we do this over and over again until now we have a new graph, but it has the same structure as the graph that we started with. And it doesn't matter whether or not you start with a fully connected graph, it will always retain its structure. And again, those are the 3 feed-forward neural networks. There are 3 of them per each layer of this message passing neural network. Okay, I guess the third thing. So the first thing was Sophia, and the second thing was the message passing neural network. The third thing that was really important for this work is transfer learning. And so I recommend if you come across a very difficult problem, let's see if you can come up with an easier or related task at first before applying your machine learning to it. So in our case, the interaction we're working with is extremely short range and very strong. So I plotted on the left on a log scale the pool of interaction here in the black dashed line, and then a bunch of different interactions with all of these different interaction parameters that we use in the paper. So compared to the pool interaction, obviously it's much more short range. But this is really the source of a lot of numerical instability in our calculations. So this was the hardest thing for us to get over. So what we ended up doing is starting our training on a softer interaction, which is still very short range, but we start here with a larger effective range, then we cut it in half again, until we reach a small enough effective range where we can do this extrapolation to 0 effective range. Just keep in mind, this is only with 14 particles, so this paper was more or less just establishing the method we plan on using once we work our way up to larger systems. Any questions at this point?
Comment that if you were known, it's quantum integral reward that will tell you this is solved by adding cast condition by hand.
Yeah, so we don't, that's a good point. We don't do any custom condition because that's a specific, specifies what Hamiltonian you're working with in the first place. So our goal is for this ansatz to be as general as possible, very minimal changes for it to transfer to nuclear systems like nuclear matter and nuclei. So we don't want to do any engineering on that, just basic symmetries and boundary conditions. One also really nice feature about this ansatz, it's independent of the particle number. So we worked out exactly how many parameters you need. The only model dependent part is the spatial dimension here. Everything else is a hyperparameter. So here are the numbers that we actually used throughout most of this work. It ends up having 8,500 parameters. I don't know if you think that's a lot or a little, but yesterday I some people were using 5,000 parameters for MNIST and things like that. So I think that this is actually scaling pretty well. And again,
So I'm kind of intrigued. So do you have a method that does not scale at all with particle number?
Mhm.
So where's the catch?
Okay, well, it doesn't mean that you don't need more parameters when you go up with the number of particles.
So the number of parameters scales.
The number of parameters is constant with the number of particles. but you may need more hidden nodes, for example.
Okay. So in that sense,
In order to
that's.
capture.
what's-
But we've gone up to n equals 38. Oh, wait, is that the next? Maybe that's not, yeah, okay, so we've gone up to n equals 38 so far. What we did is we started at n equals 14, used that as an initial point for n equals 16, n equals 18, and so on and so forth until we reached 38. We could go theoretically more and more. And that's something we do plan on doing in the future, and then also doing the extrapolation to zero. So this is just a huge application of transfer learning. In our next paper, we can just point you to, this is our general strategy. On the right-hand side is the actual optimization curves for a few different particle numbers. So you can see we started off a little bit closer to carbon gas energy, and then we work our way downwards, and then when we switch to a higher particle number, we jump up a little bit, but not quite as much. And for computational scaling, this is just completely empirical, and I'm using this 4 GPUs here. And our scaling seems like it's less than n squared. And like I said, we just wanted to impose the most basic symmetries boundary conditions. And so we can very easily transfer this to nuclear matter and nuclei. So for example, for nuclear matter, in addition to just changing the Hamiltonian, we include isospin into the one body input to that message passing neural network. And we also add the products of the isospin projections into the 2-body input. That's all you need to do since we have the same periodic coverage here. For nuclei though, it's like a couple additional steps. So for the boundary conditions, instead of having like a minimum image convention, applying this periodic treatment for the distance variables, we just have a defined Gaussian envelope. And for nuclei, since we don't have translational invariance anymore, we input in the positions themselves into the one body input and also subtract the center of mass concentration. That's all you really need to do in order to make it work for nuclei.
Can I just ask?
Yeah.
Is there anything new in this that makes non-local Hamiltonians successful?
I'm a little afraid to say anything about non-local things because we haven't tested it.
I can tell you something. So the non-local, if you were to use non-local Hamiltonians, and but keep using a coordinate space as your Hilbert space, then when you compute the local energy, the kinetic energy is diagonal, of course. But the potential, sorry, I think it's back. You can do that, and the kinetic energy is still the derivative because the Hilbert space is x. But then when you compute the potential, we integrate over x prime, pretty much the same way we compute the momentum distribution. So it's going to cost more, but it's not impossible. Now there is another approach that you can do the whole thing same momentum space. In that case, the kinetic energy is diagonal, but the potential energy is highly diagonal. And that will cost a little more. So basically, for each pair, if you start from some momentum P1 and P2, you need to check for all momenta that are connected to P1 and P2. So you conserve the center of mass, not the relative. So it costs, computing the local energy will cost more. But we're working also on the equation number formalism. So ignore all this thing and just it's like a tensor network. So the network has inputs the equation of a given determinant and then gives you the answer. And that's how we do it. You can do the shell model, the shell model.
Okay, but all of that is there's nothing new. That was all true before.
Well, in diffusion though, you have to do imaginary propagation, and if you were to use non-local potentials, that would cause a strong sign problem. And here we don't have it.
Okay.
So it's more more computational intensive, but it can be done. Whereas earlier you would have really a huge sign problem, so it couldn't be done.
Any other questions in this section of the talk? Okay, so I skipped over a lot of the motivation for why we're studying these systems, but you can check it out here. But since this is a symposium and not a conference, I wanted to talk about some very, very There's a lot of things that we could do with these neural quantum states that have not been done yet. But people have looked at excited states just very recently, but we want to think about some other methods. So one thing that we were thinking about over the last week is, can we rederive stochastic reconfiguration, but instead apply it to 2 or more different states at the same time, and under the constraint that all of those different states are orthogonal. So it turns out it's much easier if you start with an orthogonal state. And this kind of makes sense because people have looked at BMC studies of excited states. And so what they do is orthogonalize the states, do imaginary time propagation. And they found that they stay roughly orthogonal for a surprisingly long time. But eventually you will have to re-orthogonal. But it would be nice if we could just orthogonalize once and then have our optimization scheme take care of maintaining that orthogonalization. So, okay, I did the math. It's very similar to a regular stochastic reconfiguration derivation. And so what you end up with is, for 2 states, you end up with a block matrix equation. If you ignore the off-diagonal terms and just look at the diagonals here, that's exactly the quantum Fisher information matrices that I described before. These are the changes in parameters. And then these are the gradients, the same ones that I mentioned before as well. Now, because these are coupled though, we have these off-diagonal terms. And this equation actually looks very similar to the quantum Fisher information matrix. I won't go into it. But these off-diagonal terms is where the constraint comes into play. I have more here. So it turns out that these off-diagonal terms has an extra factor of delta tau. So this makes sense that these are smaller in comparison to this delta, or the diagonal, because this has generally been found with previous BMC studies. The problem is that these off-diagonal terms contain expectation values of the Hamiltonian squared, which in position space would be very expensive to compute. Okay, let's ignore that for now and let's just keep going. So we think about how we can orthogonalize the states. So one possible option is by taking snapshots, kind of like what a lot of people here are doing, taking snapshots of wave functions, and then constructing an estimation for like the lowest lying states by the diagonal in the subspace span of this snapshot. So say I do this, I solve the exact eigenvalue problem, and then I try to find a change in parameters that would best reproduce this, because that way I don't have to re-orthogonalize it. I can use the method that I described before. So what's nice here is that we end up with a similar kind of structure as before. This part is actually exactly the same. The difference is here, and then we have a bunch of the coefficients on this side. So here, the important thing is that no Hamiltonian here. So I don't think that this will be very expensive to compute, but okay, anything can happen once we actually do this. Okay, and if this doesn't work, we could just maximize the overlap with these states. You know, once we find the estimations of the ground state and the first excited state, we could just train it in a usual way, the overlap. So yeah, so we went over, you know, diagonalizing the Hamiltonian. We could do that. We could minimize the overlap between these 2 initial states. That's also possible, or maximize this. We could also try Gram-Schmidt. There's a lot of different ways that we could try getting an orthogonality with these mathematics.
Generally, you probably wouldn't want to use Gram-Schmidt, though.
Yeah, oh, I don't. That's like why I put it on the last
Sorry.
thing, but it's an option, but I also wouldn't like that, because then the later states will all be dependent on the parameters of the states before. And
Yeah, just mean numerically, if you
Yeah.
want to organize, then you better be some householder or.
yes, it's not stable. But I just put it down because everyone knows how to do Gram-Schmidt.
And if it's only 2 states, it's probably yes.
Yeah.
Probably not so risky.
Yeah, once we do this, we'll just do like a very simple one-dimensional fix for see if it works. We talked about going to momentum space. I think this would be very cool. So the kinetic energy would be trivial, it would not be expensive at all, and that's the most expensive part of our calculations right now. For the bound state wave functions we have, there would be very minimal changes, or maybe we would have to change a lot of the sampling process and calculating expectation values, but that's okay. As far as I know, nobody has done this for nuclear physics for sure.
The Neutron paper mentioned I believe that for the neutron, work done before they were using the moment space.
Or were they using neural quantum states though? I specifically mean neural network quantum states.
Yes, they did.
Oh, okay, so scratch this.
Not one thing, it's a mesh. It's a finite grid.
Oh, okay. Okay. And so, okay, another thing. I would like to see if we could just do the Faustian and momentum space. And so I saw this talk recently by Scott Wagner and his paper by Anthony Triviano and Dick Burnsall is here as well. And so yeah, maybe we can do a little collaboration with the short range correlation physics. And so I've been thinking about some other things like scattering. I'm kind of new to scattering, but I think it's very cool. And I think I don't think anybody has done this, but I could be very wrong about it. So this paper by Cohen is from the 1950s, and reading it was very inspiring. And so it became clear like how the neural network would fit into all of this. So I would try to do a very simple case first. And so the idea would be to try and handle the poles by just finding this neural network here. But it's not so simple because this pole is still going to create some problems. The one way that we did it in position space for very singular potentials would be to regularize it, obviously. And then the paper by Cohen actually describes this process, how you would do it. So this is just an example of how I would do it. And I could also put on a Gaussian envelope. Oops. And yeah, instead of the energy functional that I described before, have this other functional here. And so you have a question?
Thought on this, so if you are regularizing here with this epsilon, and Xiiln might be talking about this more, but why not just go a little bit away from the real axis and put the epsilon in the K?
Okay,
I
mean, I totally believe that that's a good way of doing it. I don't think I'm enough of an expert in this yet.
Just, yes,
to be able
since you're
to-
throwing out ideas, I mean,
Yeah.
if you don't want the singularity, I mean, you can also do like principal value integration and just get rid of it and take the limit, but I think Xiiln's probably gonna talk about it more.
Actually, in my talk, I will also talk about how those ideas can be coupled to the
Okay, very cool. Very excited. Okay, then I was talking to Christian about this idea for our Simmons. Pointed me to some other papers and maybe consider Newton's method. So I'm learning about this with K-matrix. And I think this could be very cool because we have a lot more freedom when we're working with neural networks to say what our inputs are. The very simple one would be just including two different momenta and maybe a partial weight, for example. But maybe we can try putting inputs of the potentials or the parameters of the potential as well and train it all together. I don't know. So I'm working on this code right now. I'll probably run into some issues and then figure out how to finalize this idea. And that's it. Thank you.
Thank you, Jane, for an excellent talk. Are there questions? Simon?
Yeah, I wanted to ask about for the message passing networks,
Yeah.
what the actual architecture and choice of activations. Like,
Oh yeah, so I think I had, the hyperparameters, like the width. Like, I think the width was just 16.
Mhm.
2 message passing layers, 1 hidden layer in each feed-forward neural network.
Okay.
Yeah.
What was the activation function?
Oh, it was G.
Okay.
I think I almost always use G.
Yeah, it's.
All right, other questions? Scott?
Nice talk, Jane. You responded to Ali's comment that you want, why not just put in the cusp condition? Because you want to be agnostic. But should it be true in general that those geminals entering the FAFI and as R1 goes to R2, those should always just be proportional to like a 0 energy 2 binary function?
Yeah, I think there's some like universal scaling behavior. Yeah, we could put that in, but I mean, it works without it. So, if we run into issues, that would be a way that we could solve it. But I think if we don't put that in, it kind of speaks to how flexible they are. It's learning the cusp condition on its own.
Scott?
Oh,
Can you say a little more about, like, when you train the network, I suppose you're doing some number of full model calculations, how many, if you have 1,000 parameters, how many are you doing, and how numerically demanding are like each calculation?
like you're not talking about the number of flops or anything, right?
Number of what?
You're not talking about the number of flops or anything, right?
Yeah, well,
No idea.
like if you do a full model calculation to train something, you have to do, I suppose, several.
Oh, yeah.
How many full model calculations do you do? And is one full model calculation a minute on a computer or
I would
a day,
say,
an hour?
Okay, so a full training iteration at most would take a minute, maybe anywhere from
Okay,
10 seconds, maybe 50 seconds. But that includes many evaluations of the wave function, including all the gradients and then all this stochastic reconfiguration stuff with calculating overlaps. So it's all of that is included in
what
less.
set of parameters?
It's the neural network is the variational family, so it's not like it's solving another problem.
No, but you train it. You have to do some full model runs to train it, right? I just asked about the training.
It is the full model one.
It is the full model. Okay.
Yeah. I'm not emulating a more this is the high fidelity model.
Okay, this is the. Okay.
Yeah.
Sebastian?
Yeah, I was wondering, so you talked about getting excited states. Is it in single particle coordinates fundamentally, could your excited state happen to be a center of mass excitation?
No.
Your-
I mean, well then, if it is, then you could just remove the center of mass.
Yeah, that's
Or like-
my actual
or
question.
put-
So
Put in this.
how difficult would it be to do something in Jacobi or some relative coordinates? Because you don't have that Faffian.
Oh, it
Thing
should,
anymore.
it would be very easy.
The anti-symmetrization is not non-trivial once you go to the.
Oh,
That's what, I
oh.
wonder, like, how would you do it in this framework if you were to?
Yeah, I'm not sure, but I'm not sure if it's necessary because I believe like the message passing neural network would be able to find these ideal latent space coordinates. So maybe it's discovering those.
There is no center of mass. We subtract the center of mass coordinate for each sample, so there is no center of mass excitation. The
Okay.
energy of the center of mass is
Okay.
given. In Newton's case, it is not a problem. Finite, we subtract.
Oh, it's infinite, yes, you're right. For finite, I was thinking
For
for
finite,
finite.
we subtract it, so the kinetic energy of the center of mass is always 0, both for ground and excited states. So that's not a problem.
Okay, yeah,
I was just gonna ask about for the excited states of the orthogonality that you're trying to enforce. How frequently do you have to enforce that? Are you enforcing it after like each training step or?
I would like to try and explore every avenue for orthogonalize one.
Yeah.
And then have the training process maintain that orthogonality. I don't know if it'll work though.
Yeah, I wasn't sure. I mean, I knew that it was kind of a sketch, but I
That
wasn't
is
sure.
always something we can fall back on. That's something that
Okay.
people already do is re-orthogonalize it for 10 or 100
Yeah.
steps.
That's really cool. Okay.
All right, let's thank Jane once again. Responding to you.
Yeah, of course.
Okay, all right. Okay, our next speaker is Alessandro Lovato from Argonne, and he'll talk about variational learning nuclei and hypernuclei.
Thank you, Dina. Thanks for organizing this very interactive meeting. Right, so thank you, Jane, also for introducing most of the techniques so that I can focus on some of the results that they primarily by a student in Trento, which is partially supported by STREAMLINE. I don't know why it doesn't change slides.
Okay, maybe because I have to click it, I think. Yeah.
Okay. So the idea here is that, yeah, the Hilbert space of the model clearly explodes exponentially, but then there are symmetries and features of physical states that actually reduce the number of states of interest to a corner of the whole Hilbert space. And I mean, Minfield already does a great job in solving atomic nuclei and nuclear systems. So I hope that this if the actually valid is some empirical evidence, to say the least. So Jane already went through it a little bit, but I think it's useful to iterate. So in order to reduce the complexity of the problem from exponential to polynomial, one needs at least two ingredients. The first and foremost is to design a wave function psi that doesn't scale exponentially with the degrees of freedom of your problem. So it cannot scale exponentially with the size of the Hilbert space, and it cannot scale exponentially with the number of particles. This is clearly different from configuration interaction methods in which you expand using Slater determinants, and the way you can put A particles into N states is a binomial coefficient. You don't want that. And then there is a second ingredient, which is that we need to sample the Hilbert space, because the Hilbert space itself is exponentially large. So if we were to do numerical integration, say, we would get the exponential scaling back. So neural network quantum states are basically based on the idea that we can replace the wave function of the system, independent of the system, actually, by a neural network. And this neural network has to obey the symmetry of the system. So if it's fermionic, when exchanging two particles, one needs to get a minus sign, and it has to be a complex number in general. And then we train the network, and we compute the energy by sampling the Hilbert space. This X here is general. It could be the coordinates, it could be the momenta, it could be working in the equation number formalism. Then it's like strings of zeros and one. And then we optimize the variational parameters, as Jane explained earlier, by basically taking the derivative of the energy, but also taking into account the curvature of the Hilbert space. So because of the fact that two-wave functions that only differ by a global phase are actually identical, immediately we realize that the metric in the Hilbert space is not Euclidean. So basically the difference between two-wave function is not just the squared sum of the difference of the parameters, but there is more to that. And that can be encoded in the quantum Fisher information matrix. So let me, all this on the nuclear physics side, we are using somehow pilot CFT inspired potentials. And so it's Hamiltonian with a kinetic coordinate space. It's an Hamiltonian with the kinetic energy 2 and 3 body forces that somehow capture some of the complexity of realistic nuclear forces. And these potentials are based and inspired by binary CFT, but are not really, strictly speaking, binary CFT, because we take a finite range and we fit both the coupling and the range to reproduce the scattering length and the effective range in the NP channels, both the Juliet and the singular. And for the three-body force, we do a similar, we follow a similar procedure. So if we just, the three-body force is characterized by a repulsive constant CE and a range. And then if we just fit the binding energy, say, of Triton, we get a relation between the range, R, and the coupling constant. And typically we pick values in this region because they reproduce as well. They can reproduce helium-4 as well. So we take helium-4 as an observable if you want to break down this presence. We could do a better job, but we just wanted a semi-realistic Hamiltonian to play with and see whether all of this technology worked. And what we came up with, so that the problem is that you want to design a wave function which is antisymmetric by design, because if you don't impose thermal antisymmetry, you converge to the boson ground state of the Hamiltonian, which is almost always the ground state. Not, you can design crazy Hamiltonians that admit a fermionic ground state, but that's not the case for nuclear physics. And so we wanted to design a wave function which was which respected thermal antisymmetry, but it was also universal. We wanted a universal approximator for antisymmetric wave functions. And we took inspiration by this work in condensed matter physics that goes under the name of hidden fermions. Here, the idea is that if you were to do if you had 4 particles and 4 states and do a Hartree-Fock calculations in first quantization, you would just have these metrics. And your wave function is the determinant of these green submetrics. Within the hidden nuclear approach, basically we're adding rows and columns, meaning that we're adding fictitious particles, y1 and y2, and fictitious states, chi1 and chi2. One can show that these ansatz on the lattice is universal. So you can represent any antisymmetric wave function in this way.
Alessandro, just a curiosity, because many of you may know the problem for the first author. The R stands for Robledo. And many of you may know Luis Robledo instead. That's actually the son of Luis Robledo.
Yeah, also Antoine Georges is one of the authors.
So why do you need the hidden variables and nucleons here?
Sorry?
Why do you need these extra, wave functions and nucleons?
Oh, because a single state of determinant is not a universal approximator, right?
Yes, okay.
And this one instead is.
What can you define universal here? Because it would be antisymmetric just to determine, right? It's just the normal coordinates. It would give you an antisymmetric state, and if you expand.
But it's not universal.
But what does universal really mean?
That you can express any antisymmetric wave function in this way.
Okay, you're saying Slater determinants alone would be restrictive.
Oh yeah.
Because it captures correlations. Now.
Oh yes. So that means that any antisymmetric wave function can be written in this way on the lattice. Okay, so in the continuum there is no truth. So we are kind of heuristic here, and we try and see if it works. But on the lattice there is a rigorous truth. I mean, of course, the underlying assumption is that you have a neural network that can represent the orbitals, and the neural network is universal. But that can.
And this is the x's and y's. They have the spatial and spin together.
Yes. Yeah. And this is the pictorial representation. So the real 3 nucleons are very, very correlated. So a single Slater determinant is not enough to represent their wave function. But then if you introduce additional degree of freedom, then one single Slater determinant is enough to describe these 5 things. And a little bit more on the learning. So as Jane said, what we do, we don't just use Adam. What we're actually trying to do is, this is going to be relevant for the discussion at the end of this talk. We start from some set of parameters P at time tau, and then we apply the imaginary time evolution operator for a short time. And this defines a sidebar D of P tau. So it's a new state. And then what we do, we basically change the variational parameters so that to maximize the fidelity between this state and the new one. And this is pictorial, this is what happens. And actually, we don't care about the norm. That's the other trick. So because of our global phase or global number, we only care about the angle between these 2 vectors, and we minimize it. And clearly, one can see that one can apply this strategy to the real-time evolution as well. You just need to replace delta rho with I delta t. It's more complicated than that in practice, but that's the idea. So that's what we did initially. We tested the spectrum, how well we did reproducing light nuclei using this simplified Hamiltonian with just, I would say, essential Hamiltonian in a sense. It only has 4 parameters in the 2 body sectors that are fixed, on scattering length and effective ranges, and 2 parameters in the 3 body that are fixed here. And then everything else is prediction. And I think we do remarkably well for being such a simple Hamiltonian. And and the power of this hidden nucleon wave function is also that we can do open shell systems with just one determinant, right? Because since it's universal, it doesn't only account for correlations, but it also accounts for deformation. So yeah, so that is, I I've always hated French product with shift coefficients from the bottom of my heart. I hate all of them. And so I'm so relieved that this is, didn't work instead of have to learn that. Anyway, so in addition to ground state energies, we also included magnetic moments. And the cool thing about that is that the neural network quantum state doesn't know anything about the polarization of the system because there is a degeneracy. So in order to measure the magnetic moments, we have to add an external magnetic field and polarize the nucleus. So we first do a training, and then we add a small magnetic field to change, to align the polarization, to anti-align the polarization of the nucleus with respect to the magnetic field, and then we measure the magnetic moments. We turn off the external magnetic field, of course, and then the nucleus stays there, and then we measure the magnetic moment, and the experiment is really good. So basically, since there is no, I wanted to stress that this is a good indication that the neural network is learning the shell structure of the nucleus. Because we start from from a hidden nuclear ansatz, which is completely agnostic to shell structure. There is no spherical harmonics, nothing. It's completely random. And when we train it, they actually learn the shells. Then we moved on with it with Bryce, neutron mass calculation, but I will skip this. So the first goal that we said in Streamline is, okay, we want to extend this to medium mass nuclei. So we did calcium, and we can do much bigger. We can go up to germanium now. And Bryce actually has been the driving force behind this, and with Corey. So now the code scale to multiple GPU nodes, and we can take advantage of Polaris. And this was done, I think, on few GPU nodes, I think less than 10. But I mean, again, yesterday we were discussing about putting together maybe a proposal and submit it to the LCC code. And these kind of calculations are ideally suited for this kind of proposals because we are looking at something like 100,000 GPU hours per year. So this costs something like less than 1,000 GPU hours. So that's kind of the ballpark. And again, this Hamiltonian does pretty well with calcium as well. Okay, we didn't touch the parameters, so I think this is consistent with what Dean did so far with a similar method. And then the second goal in Streamline was to use more realistic potentials, and Anthony Tropiano has included charge independence breaking and charge symmetry breaking in terms of Hamiltonian leading order. So now we can reproduce also NM and TP scattering. The old is the orange, the one that we are using now. And we fit them, we wrote this code in JAX with autodiff, so we can differentiate the phase shifts with respect to the parameters of the potential automatically. So the optimization is very fast. And we can do Hamiltonian multi-random is very fast. So now we can reproduce the experimental phase shifts with high accuracy. Now the goal is to implement this into our code. And then this is also something I wanted to mention in this talk. It's hypernuclei. This is a bound state between an ordinary nucleus with one or more hyperons. And in this first work, we only consider single lambda hypernuclei to begin with. So we go from carbon 12 that 6 protons and 6 neutrons to say, for example, carbon 20 lambda, which has 6 protons, 5 neutrons, and 1 lambda particle. So our goal, of course, is also to compute the equation of state of neutron star matter with hyperons, because we know that at high density, if you only have protons and neutrons, you have big Fermi pressure. But at the very moment that we create an hyperon, that one basically is a different kind of particle. So the Fermi pressure of hyperons is very small. So how to reconcile stiff equations of state with hyperons, that's still an open question. And we want to address it. And yeah, I mean, we basically start from a similar final SFT or contact Hamiltonian for hypernuclei. In that case, we have to fit the lambda nuclear potential, which is projected into spin channels. And we fit again the scattering length and effective range. We also have a lambda and then 3-body force with 3 different low energy constants. And the parameters are determined by fitting very light hypernuclei. And we do that, Andrea Di Donna is the student in Trent that did that. And they built a whole machinery to do this fitting very efficiently using both neural quantum states and the stochastic variational methods. And now we have distributions of parameters because now basically the binding energies of hypernuclei are known with some statistical accuracy. And we have samples of this Hamiltonian that basically reproduce these binding energies within the statistical answer, the experimental answer. And then he came up with an ansatz for the wave function. So here the idea is that there is no term mixing lambda and nucleons. So we could anti-symmetrize lambda and nucleons, but we don't need to. So basically, the wave function is the hidden nucleon ansatz for the nucleons times a factor that is permutation invariant under nuclear exchange, but it's agnostic to any symmetry for the lambda because it's a different particle. So that's the simplest thing one can do. And this is what we obtain. Sorry, this figure is not very clear. We need to change it. So we use these energies to fit, and these are the hypernuclei we predict. So the experimental is the blue, and the quantum Monte Carlo, this is the fit, this is prediction. And as you can see, I mean, we do a remarkably good job. I mean, there are some differences, but these are binding energies per nucleon. I think the agreement is pretty good for being such a simple Hamiltonian. Yeah. And we also compute radii, single particle densities. And these are normalized, and this is basically the lambda and the nucleon. So for light nuclei, basically they can all occupy the S shell, but say for oxygen 15, basically the lambda always occupies the S shell. So we will see, for light, very owing to the nature of the interaction, for light nuclei, typically the radius of the lambda is larger than the radius of the other nucleons. But then for higher mass nuclei, it's the other way around, because again, the lambda can be inside the nucleus without any problem. And now some rough ideas. This is also part of STREAMLINE. We want to do real-time quantum dynamics. And of course, this is the prototypal exponential problem. And this is very relevant for a bunch of things in nuclear physics, including fission, fusion, and lepton nuclear scattering. So with Xiiln, we started really writing things from scratch because Xiiln is an expert in time dynamics. I've never done that in my life. And they only did this kind of stuff in relativistic quantum mechanics. I don't have any idea to do that, how to do that relativistically. So I have to read everything from scratch, reading papers, old papers and stuff. But anyway, the idea is that we want to compute this response function, which is ground state, car current, final states with an energy conserving delta function, which would be En, sorry. And then say, for example, for the dipole operator, we want to use then actual currents like charge and density currents. And then a way to do that, it's basically to compute the Fourier transform of the expectation value of the dipole operator evaluated in a real-time evolved state minus the unperturbed one. There might be some missing factors here. I'm still trying to adjust them, but I think we are right. So we derive the whole thing with Naive time, so it should be fine. So this is the idea. The time evolved state is given by this. So we start from the ground state of the system, then we apply a boost with the dipole operator, and then we evolve with the nuclear Hamiltonian. Now we have two options here. We can use the time-dependent variational principle to evolve side zero with this H prime, which is basically just a boost for a very short time b. And then, or we can actually learn the ground state by minimizing the energy and then maximize the quantum fidelity between the boosted state and some unknown state psi. And then we will carry out the real-time evolution with the nuclear Hamiltonian by again maximizing the quantum fidelity between psi p, and then unitary evolution operator applied and psi p delta p. And we can do this either actually maximizing this, or we can use a second order approximation of this quantity, which is again identical to what we use for doing imaginary time evolution, but in real time. So these are the prospects. We don't have results on this yet. We are working on the harmonic oscillator to begin with, but hopefully next meeting we will be able to show something in this. And then there is some work that Xiiln, I think, is going to mention. So, thank you.
Very much, Ali. Very, very nice stuff, Sebastian.
Yeah, I had some questions. It's very nice, very impressive, especially the scaling that you can run with this. I have some questions. I think there are some timeless calculations within resummed effective range. I think Lenski and Burris went up to 6 particles or so, maybe with hyperspherical. And I think Thomas, and who was the student who did it at the time, they have some couple of factor things.
Yes.
I wonder how do your results compare in the few, and I think they went higher, like maybe oxygen or something that would like to see.
Yeah.
It's not the same potential because
No.
that one takes the C2 term and resums it into a leading order potential.
So yeah, so what we did, it's not strictly speaking ion density, because in that case you need to do leading order and then to take the derivative of infinity. And in that case, if you do the next leading order to the same thing, then you have the linear bound, and then you can fit the effective range of the scattering length at the same time, unless you do the next leading order in perturbation theory.
True, if you keep your regulator low, then you can, right? And
Yes,
from-
so in that calculations by Thomas, I think Thomas Havenbrock, and there was a student. I forgot the name.
Yeah, I forget her name too.
I forgot the
I
name,
know,
yeah,
I
but
I
they
know.
showed that there are some combinations of regulator. If you don't go too high in the regulator, then calcium, then oxygen 16, and I believe calcium 40 is stable against breakup.
Yes.
What we found in our original paper doing just a leading order, we found that oxygen 16 was unbound with respect to 14 and 4.
Right, but okay, so, but you're doing, so in principle, you're fixing the same physics, right? So they fix a C2 term to get the effective range, you pick your regulator at the point where you have the effective range, more or less, right?
I'm doing even more phenomenology than what they're doing, but yes.
Probably, but then,
Right.
so that you're saying already makes a difference whether oxygen is bound or not?
Yes. Yes, that makes a big difference. So getting the range, and also, maybe I can show you this. This is neutron matter, very low density. The band, the green is using a bunch of different ion fluid potentials, say argon 18 plus urbanine, local ion forces. They're all very close, of course. I mean, then zero density limit, everything depends on the scattering length only, right? But if you do ion SFT with an Hamiltonian that reduces both the scattering length and effective range, you get the blue. If you use another ion SFT Hamiltonian, which only reduces the effective rate and the scattering length, you get the orange. So at very low density, of course, we agree. But then there's
Yeah, I mean, this was actually very nice.
the range seems to be very important.
This is the effective range for the.
Yes.
Right?
Yes.
Yeah, so absolutely, but this is quite impressive that with just the NLO, you get that close.
Yes, that's not even a complete NLO in the sense that it's NLO only in the S wave and using.
But that is complete
it's
because the P wave comes
Yeah, yeah.
higher.
High. And in fact, yes, there is over that comes in one, but yes, I agree.
Other questions? Yeah, Jorge.
So is there any indication in the 314 that the use of the lambda nuclear system or some stiffening that could help the equation of state and high densities, or there is no evidence of that?
Okay, so here we are using, this is very, very low resolution because it's a pilot CFT if you want potential. So we will not use this Hamiltonian high density matter. It wouldn't make any sense. But at least we wanted to check that our methodology, our framework, these answers, for example, and would allow us to reproduce hypernuclei. Then if we really want to do hypernuclear matter, we did it in the past with the standard quantum Monte Carlo. But then you have to use a higher resolution interaction because otherwise it will break down right away. So here I think I need to think a little bit about it. I don't remember exactly. This is overall. I think it's overall repulsive. This contribution, I'm pretty sure, but it is so low density, so low resolution that I cannot make any prediction.
Yeah, sure.
Yeah, about hypernuclei. So you show some densities which are not so high. Yes, so I see that it goes up to 0.06.
Yeah, so these are normalized though. So the integral of this is 1. It's not 4, say, or so you don't take this number to see.
Yeah, but I think it is a good estimation. I mean, a good order of magnitude of density. So when you plan to go for in dense matter, do you plan to exceed these densities? Do you plan to predict something out of where experimentally it is controlled?
So the density that we're playing here are not an indicator of the breaking scale of the theory in matter. So for that, one can estimate the Fermi momentum, for example, in matter, and see whether this is twice the pion mass. Sorry, it's more than the pion mass divided by 2, for example. That's something. That is what the breaking scale of my effective theory, even though I'm not really doing an effective theory. But so I wouldn't trust these calculations in matter beyond that limit, independent of the density I'm getting here. Okay.
Okay, other questions? No, let's thank Ali once again. I don't want to leave it this way though, so it's. I'm trying to make sure I did. I want to try to download it to another website. Download. It's not the, I want to use it with the correct viewer. Let's go. Let's see that. Yeah, that's the point. I think we're good. Let me just check. Yeah, everything's good. All right, so we have our last speaker of the symposium, Xiiln Zhang from FRIB, and he'll talk about emulators for quantum continuum states.
Yeah. It's not sleeping, so maybe.
Yeah, I have to click it. I just need to click it. Yeah.
So first of all, thank Jim for organizing this. I wish next time someone will take some responsibility on behalf of you. I'm going to talk about emulators for continuum states, and I think somehow eventually it turns out the scheduling was really nice. So I'm the last one, and I can take advantage of the previous talks and get into more details about what I've been doing the last 1 to 2 years. So the outline of the talk, the real time. So now I start talking about two types of emulators for continuum states. One is the one that people are most familiar with, that's called the real energy emulator now. And the second one is the complex energy emulators. And in the end, I'll briefly mention something like I'm playing with some other people at FRIB, emulators outside of quantum physics, and summarize it. Just very quick to say, emulators is essentially about a problem for interpolation and extrapolation in some kind of Planet space. But the definition of the Planet space is what you give, okay? And the emulators we are talking about are really nice when you go to the situation that you have a non-trivial dimensions, a little bit higher dimensions like 10, 20, or 100. Now, so very quick recap about the real energy emulators that Joshua has also discussed. Suppose you want to look at these Schrodinger equations. Now the situation different from bound states is the eigenenergy E is fixed, is what you give. And at this particular real energies, you want to solve these differential equations. Right? And for emulations, Hamiltonian has some parameters. So you want to emulate these solutions and also observables associated with these solutions for this parameter space, theta parameter space. Now, the IBM method, reduced basis method, basic idea is that suppose you have some snapshots at a few points, there are different ways to sample those training points and use ANDAD of these to construct tri-solutions. Now, so the main point here is that the true or the effective dimension of your solution manifold is low. So then use the number of this NB here number is also low, typically 10-ish or 100 in all these previous cases. So now the problem is finding out those unknown coefficients, okay, for different theta. And because NB is low, so the problem is very, very easy to solve. You have a small matrix problem, give you fast emulators. So he tested it in various studies now about two-body scattering problems. And there's a very nice review of modern physics. It's submitted a review of modern physics. You can look in that review paper to find out all those previous studies. And also there's other reviews, nice reviews too. And you can trace them here. Now, 3 boson we did a couple of years ago. This just really straightforward generalizing this idea to 3 boson systems. So for STREAMLINE, we are applying it to emulate nucleon deuteron.
scattering. So it's supposed to be a important work because it will allow us to have a new calibration of three nuclear interactions. But with all those new developments from band collaboration based in UQs, and also the important thing with emitters is that you can analyze a lot of ND scattering data, which you cannot do before because the calculation, 3-body calculation is expensive already. Of course, the exciting futures will be like applying all these kind of things in deuteron nuclear scattering. So in the line of what Pablo or other people have mentioned about neutron nuclear scattering. So 3-body emitters can also do those things for more complicated processes. So these are tables summarizing the performance of these 3-body emulators. The key thing here, just referring back to this statement here, the time is a millisecond. This millisecond time scale has popped out several times in this meeting because you're really dealing with a very small dimension linear problem.
So you need one question. So do you need a reduced basis for each energy and each angular momentum?
For each energy, yes.
And the angular momentum?
If you do partial wave, yes. Okay, each partial wave. Yeah, right. Yeah. So to suggest the status of what is happening right now, so we are developing a CLT formalism, and the group actually has expertise in a version approach for ND scattering, but high fidelity calculations. For example, they have a review paper and just highlight here. So they have been applying the variation approach for studying ND scattering for a long time. So we are going to take advantage of that and use that as our high fidelity calculation for training purpose. So plan to have some results before the end of summer. And also, I believe Christian and the student Joshua are developing, have interest in applying the tools he has mentioned to these cases. Now I really want to get to this one. So second type, complex energy emulations. So before talking about emulations, I really want to talk about, spend a little bit of time, talk about what is the type of method people have been doing to solve continuum problem, which don't get covered much. So the issue here is this. So we have a Hamiltonian, okay? It's divided in infinite volume space, and we know, physically speaking, it has a spectrum. It has a discrete size bound state, okay? So the eigenvalues are discrete, and up to some threshold, beginning from that point, all the energies are allowed. All the real energies are the eigenvalue in principle for the Schrodinger equations. And then people think about one particular type of approach is how do we digitize this Hamiltonian operator to a matrix? And you immediately see the difficulty here. As long as you make it to a finite matrix, and if you want to calculate something like these, okay, this is some source vectors, and you apply this resolvent, mathematically called it resolvent, we call it Green's functions, and then overlap this with this vector with some other sources. So these are very important calculations because it covers the response function calculations like nuclear scattering, even optical potentials, all kinds of things are related to this kind of quantities. Now you immediately see that as long as you make Hamiltonian finite dimensions, okay, so this quantity will become a bunch of poles, right? So any question about that? It sounded trivial, but actually this kind of get lost in a lot of discussions. So, and what does that mean? So, if you have a finite matrix, you only have a pole structure for this energy dependent for this quantity, right? But in reality, that H is infinite dimensions. So it actually above the threshold, it has infinite number of poles. And the consequence of the infinite amount of poles is the coalescence and become branch cuts. There's a very dramatic difference between these two sets of results. So the problem is that very immediately, like if you have this, right, you calculate these response functions or this kind of quantity, imaginary part, at real energies. And if you're Hamiltonian, if you make it the matrix, and if you still Hermitian, you will have a lot of poles here. And you have a physical bounded poles. And you calculate response function, you see it spikes. Okay. But the real physics is that the response function is actually quite smooth. So if you have some threshold here, it will be strictly zero away from the bound state, and start kicking out, become non-zero, gradually increase. And if you have a nearby resonance poles, you will have resonance features like that. Okay, so the physics is actually quite much simpler in some sense for continuum physics compared to if you have a million dimension matrix. A million dimension matrix, you will have a million poles along the real axis. You have all those spikes.
So you're probably going to get to that, but in practice, people would either do a Lorentz integral transform, discretize the continuum, the bound set method with the complex energy. I suppose that's what you might be mentioning, but
Yeah, so this is actually connected. The reason people do complex energy or Lorentz transform is because they know the quantity they calculate on the real axis is chromatic. So they go to the complex plane to find a place that you have become sensible and then extrapolate that information to the real axis.
but also in the many body sector, like Sonia and others, they only have discrete spectra, real or maybe complex if they have some continuum in their basis. And then they really actually only get some discrete levels for the response function. They're not trying to get the actual experimental result back because they would not know the normalization. They just basically smear it with some Lorentzian, right? So what exactly is the, I guess I don't understand what exactly is the point.
The problem is,
Just trying to
I'm
make-
trying to point out the problem is that, so, because people have mentioned about, emulation matrix, like small matrix. But even before getting to about, thinking about emulation, for continuum problem, this Hamiltonian operator is infinite dimensions. Even for high fidelity calculation, if you think about digitizing in some way, a very high dimension matrix. The immediate problem is that this kind of quantity you calculate on the real axis is not physical, no matter how you do it. So the difficulty people say, like for the continuum problem is tails not right, okay? If you can like imagine, actually, so the sources are compact. So this solution and this quantity actually only cares about the internal wave functions. It's not actually about tails. It's kind of provocative. But, and then another way to say that if you have a good basis to have the right tails, as long as it's a matrix, you still get these kind of difficulties. You cannot get around with it. So, but then this is like, this really leads to a second, like a big type of way to solve continuum problems called non-conditional quantum mechanics. So I'm trying to expose what is the real essence of these approaches. And in the field body methods, typically like we solve the differential equation, we want to explore the complex plane, a very well-known method called contour deformation, okay? And actually this method all connected to that kind of idea and apply to the many body settings, okay? So then what we does is that now it has a good basis that breaks the hermicity of Hamiltonian. So the eigenvalues are not real anymore, okay? So if you look at this particular method called complex scaling method, some toy problems and look at the eigenvalues. So they have these kind of eigenvalues. Okay, so it's like they have a very dense number of holes trying to mimic some kind of branch cut. They have a multiple branch cut, they have multiple thresholds, okay? So this is a part of the spectrum. And the other one is a physical state, people call it physical resonance state, something like this. Okay, so most of them don't have any like unphysical poles or eigenvalues along the real axis anymore. This is one advantage of this kind of method. And the threshold behavior is systematic improvable. So if you think about the response function, so the one thing is that this is a big point that people need to keep in mind. The Hamiltonian eigenvalue, we talk about spectrum, is actually very closely connected to the observables. Okay, so you can see that, right? So these observables is basically a whole summation of a contribution from different spectrum, different eigenstates. So this is why by just looking at a spectrum, you can already see a lot of things about observables. So now, like if you have nearby resonance eigenvalues, you will have resonance poles. So then if you look at response function on the real axis, you have a bump, you have a peak. Now all these ones are trying to improve mathematician knows like this whole structure adding up together is trying to get you some very good behavior about threshold. So this function is very non-trivial. It's 0 all the time and suddenly turns on. So it comes from square root. And something similar like Patrick mentioned in his talk. And the other thing is that now the physical poles here, so this is a branch cloud, the physical pole here, and then the bounded pole here are actually on the same Riemann sheet. But what does that mean computationally? So if you have a branch cloud on the real axis, and if the code defines that way, so then whenever you capture anything in this complex energy, okay, you will only see the bounded poles because the resonance are hiding behind on the secondary machine. But now if you push away, rotate this branch cloud, suddenly this part of the region and the bounded are on the same Riemann sheet. So your code actually will see the pole come from resonances. Okay. Of course, if you have poles at this region, it must come from the eigenvalue of your Hamiltonian, but the Hamiltonian defined in a very non-trivial way. Now, so this is the goal or the consequence of this method. And keep that in mind. Okay, I will come back to this point. So now I'm going to talk about complex energy emulations. The original motivation was very simple. So if you look at the Schrodinger equations for in general Schrodinger equations, you can make it inhomogeneous, as mentioned in the previous talk. And it turns out the important thing is that if you think about energy complex plane, when this energy complex in this region that has some finite imaginary part for the energy, the solution here is actually like a bound state. So this is in the spatial coordinate, in the mobility space, that means those poles get smeared out. Okay? You don't have the delta function anymore. Now, so then the issue is that how do you extrapolate this information you get back to the real axis? Okay, this is what I want to calculate. So that's the different ideas people have tried. And of course, going through this route, you can extract continuous freedom from bound state-like calculations. Okay. Now, of course, for emulations, so now I want to use emulation technology to do that extrapolation. The other point is that you can just add extra dimensions by including theta. So you can emulate theta as well in the same framework at the same time. So back into the previous slide, I think remarkably in the last 1-2 years, I found is that this kind of emulation actually also achieve the goals of those non-emission approaches. Okay, it actually can make the branch cloud rotate and make your Hamiltonian non-Hermitian, the compress, the dimension reduced, Hamiltonian become a matrix, and because of that, we can actually start seeing the resonance showing up as eigenvalue. Yeah.
So let me see if I understand. So like the Lorentz integral plus one, for example, they basically compute a bunch of solve these equations for different values of V but with a sizable, say, imaginary line component.
Yeah.
And then they say extrapolate to zero imaginary line component by inverting the lead, but they don't use any eigenvector configuration. At that point, they just extrapolate, say, the energy.
Yeah.
In your case, you're saying we can do better, we can do eigenvector configuration, so it should overcome, outperform the lead the same way eigenvector configuration outperforms polynomial.
In the ideal case, you can directly extrapolate. And that extrapolation process is a linear algebra problem. And you know that for the lead, it's a nonlinear regression.
Yeah.
Right? And on the top of it, I mentioned the theta here. So put it another way, you actually can emulate already the first part of the LT program, which is calculating those complex energy solutions for different Hamiltonian parameters. That one can be easily emulated. Already.
Theta is the ground state of a given Hamiltonian for them. What they do, they take an Hamiltonian and psi of theta is the ground state. S is the source, it's like the current applied.
Yeah, the source here can be some transition operator on the ground state, and in the process, you can get a response function out of it.
And psi of theta is the one that wants to learn.
I'm sorry?
And psi of theta is the one that you want to learn.
Yeah, the first theta is one you want to calculate, you want to emulate, and all those things. Yeah. Okay. So I want to emphasize here, I'm talking about emulation of spectrum, actually the full spectrum, and also observables at the same time. It's not a particular state. Okay. I will try to explain that in detail later. So this is a toy model, like a Newton case, the toy model, and what is shown is the error plot for some T-scattering matrix in the complex energy plane. Okay, so you fix the scattering energy, but if you look at a resolvent operator, you have this one of E minus H. You let E varies in the complex plane. So this error plot, the blue means small error, the red one means big error. So the first plot is this. If you put the training calculation here, okay, has some finite imaginary part along this line. And you see like in general, this is the interpolation region, right? So the error is small. And those very deep black dots is where the error becomes the smallest. Okay, and those are mostly concentrated at the training. And now we start extrapolating. Okay, we start extrapolating in the composite plane downward, the error becomes bigger. But the non-trivial thing here is that you see the dark spot here, right? This is where the emulators eigenvalue are, or it's where the emulators poles for the response function are located. But then physically, the response function in this region is smooth. Okay, so you have a pole compared to the smooth function. This is where the error becomes biggest. Okay, but then it tells you your branch type, the trying to mimic branch type here. So this is what I mean that the emulator also rotates the branch type. If you don't do that, if you're in the full Hamiltonian permission, your eigenvalue will be here, your branch type is here. Now, it turns out these properties actually come from how you arrange your training calculation. So if you put a training calculation like this, okay, symmetric with the real axis, it actually will put the eigenvalue back to the real axis. So you see like the good region for emulation is here, which covers the bound states spectrum. Okay. And now you're making big mistakes for continuum physics near real axis. So another thing is like, I want to emphasize again, it's about emulating actually the full spectrum or part of the spectrum and observables. Now, so it's about spectrum, right? So if you do this, as I said, you will get a bunch of eigenvalues from the reduced Hamiltonian. And this is a plot of those eigenvalues on the real in the common plane. So this is like different trainings. You can put the imaginary part, like you can put training point about 30 and maybe away from reactive, or even closer. Okay. You see, like the resonance will be a 1 eigenvalue, and then you have all these discrete continuous states. Okay. They're actually coming on and trying to tell you that's a branch type. And because you put branch type here, the resonance and the bound state you have one, they're on the same image. Okay, and another striking thing is that if you look closely, the distribution of the poles is actually exponentially clustered towards the branching point here. So these are branching point, meaning that the threshold. So below here, there is no cross section. Above that, you suddenly have cross section. Okay, and this is resonances. You have this very nice distribution. And it turns out mathematicians know recently actually this kind of behavior. So as I said, we are basically any finite matrix calculation for the response function for observables is actually a rational approximation, something like a Pardee approximation. And mathematics has studied it for a long time, and they recently realized that if you want to use that kind of approximation to approximate our response functions, okay, our response function is kind of tricky as I explained here. So it has a branching point, which is like a square root or logarithm. So meaning that the first derivative is infinite at the point. And if you want to use the kind of pole structure to approximate that function, you are going to fail. Very close to singularities. So it's actually a very tough approximation. But they found out that this kind of approximation is much better than the other ones, like a Taylor expansion, for example. And the optimal ones is also like to have this kind of exponential clustering of poles. So I'm trying to make a connection between these kind of things people know in the mathematical literature. You can think of this as data-driven emulators. And what I found in the reduced basis method, I'm looking at all these things. And associated with this kind of distribution of poles, you will see the errors, or the error you are making. For example, like if you say, okay, I look at my instructed resonance and width, that is a residue. Okay, if you have a response function, they expand into the poles. Pole structures, you have locational poles in the numerator. Numerator, you will have residue of poles. So associated with poles, you have two quantities, right? And you see, okay, if I increase my dimension of my emulators, how the error gets suppressed? It turns out it actually goes exponentially with square root of n. Okay, and this is actually in the mathematical literature. You can also, this is about spectrum, and you can also kind of think about emulation for T matrix, for response functions at some particular test point, energy equals 2. And you can see also you have this exponential value with this particular square root of infinite dimension. Okay. Now I want to move to 3-body. You can do the same thing for 3-body. Now, if you look at emulators, so you have 2-body and 3-body interaction.
Sorry, Xiiln, can I interrupt?
Yeah.
So other than these theoretical insights, suppose I want to do a 2-body response function calculation.
Yeah.
What is the advantage from this over just plain Lorentz integral transform, say in momentum space, and you have your complex energy and you have to invert at the end? Is this something where you can get the response without inversion? Or like,
I
what's the
think it's a
game?
different way. Right now, I can only say it's a different way to do that extrapolation from complex into real axis. And if you do comparison, right, the one thing immediately you can see that LIT is a nonlinear regression, but it's trying to fit. And here is directly like 10-dimensional.
Well, no, not so much. I mean, I have a student working on linear momentum space. You just solve your bound set problem with the complex energy, and then you get this transform, and then the inversion is, if you want the actual response, the inversion is hard. But then maybe a different question, if it's about extrapolation, I think the Tuba, if I'm not mistaken, does few body scattering by picking complex energies above the real axis, and then he does a polynomial fit. So this is more, is this an
example here, this by, the reason I mentioned a rational approximation is not using Taylor expansion, it's using rational approximation or Padel approximation.
Yeah, I don't know what this does exactly. It could be a Padel. So
Yeah, so this is, but yeah. And so this method is like rational approximation is not new. But what they found is also like how do you arrange those poles to get the optimal approximation, meaning that you need the smallest number of poles to get the best accuracy.
That
So
would
this is
be
kind
in momentum space, that would be how to pick your mesh, because normally in momentum space, the poles that we have points are.
But the thing is that this is emerging, right? This is emerging from Hamiltonian. So what you can arrange in the basis is definitely different from what you can emerge from the spectrum. There are two different things. Okay, for the 3-body, you can have borrow this toy model from our previous 3-body paper. We fix, like in this case, suppose we have 2-body bound state. You have some 3-body interaction. For now, just emulation the energy variable alone, you get some eigenvalues. You can see now you have 2 branch lengths. It's because you have a diamond bound state, right? So it has 2 bound states. It's not a physical system. It's 3 boson system. You have some debound states, either shallow or the bound state. So now if you have a photon excited system, like when energy is bigger enough, you can break these bound states to a diamond and a particle. So it's like a 1 neutron separation. And then you can break it further to like 3 particles flying apart. So totally break up. So you have 2 thresholds here. So this is exactly out. And this is how the poles of emulators trying to converge to those thresholds. So what this means is that if you just look at A-body calculations, in principle, you can know where the separation energy is. And this is actually not trivial. Because typically people do is look at A-body calculation, mass calculation, A plus 1 body mass calculation. That's how you figure it out. But if you really have continuum physics, you've got to know what is the subsystem, how they behave. Now, so there's no resonance here, so these are branch lengths, these are bound states. Okay. So this is the response function. You can see like response function here, the 10 to 0, below some point. So there's a very quick jump. Now you can do the resonances, people are using the resonances. So we look at, turns out for the 3-body, so this is a short range interaction. 3-body system, S-way, you can have resonances in the situation that you don't have 2-body bounds. Okay. So then there's no threshold. If you do whole thing again, if you look at the eigenvalue very nicely, it doesn't have any bounces. It doesn't have any 2-body breakup like neutron separation threshold. You only have a 3-body breakup threshold here. And you see this blue line is the resonances. All the others are the branch lengths. So it's very important and valuable to have a global picture of your full spectrum. Now here you don't need to go into detail. You actually can emulate the full spectrum for lambda 2, lambda 4, 3-body interaction, 2-body interaction. You can get a global view. about how those points are evolved, with parameters. Now, so you can emulate bound states, residences, and also discrete, discrete branch count states. So of course, if you can identify residences, you can start tracking for parameters, for different parameters, how these poles move from bound state to residences or other way around, okay? That's what it does.
Can I ask for clarification? So for these, you do a training, right? So for the training, you pick the energy in that upper, like in that first quadrant?
Yeah.
Is that right? And then you use those wave functions to construct the reduced basis, and then this is what you get out. Is that right?
Yeah. So you have, as I said, right? I start with emulating for energy alone, but you can add the theta, right? You can add lambda 2, lambda 4, and you can emulate the Hamiltonian field force spectrum. So now also for the continuum observer, like scattering, okay, particle diameter scattering physics. So this is about the error for that continuum. Now, so this is a little bit hard to explain here. So basically, it's a validation of test of emulations. You can sample in the parameter space for your 2-body, 3-body interaction, you get a bunch of different calculation emulations. And so what is shown here is, so I'm limiting myself in the parameter space to the situation you do have a 2-body bound state. So then you can talk about particle diameter scattering. Okay, and then you can, these are 2 different trainings. You can set up, okay, I look at the relative scattering energy between particle diameter. At a given energies, I will have, so different curves correspond to different choice of 2-body scattering parameters, such that it has a given bound state, binding energy. So different curves correspond to different binding energy for the diameter. So if we just look at a particular one, a shallow bound state here. So what this does is that at each point, you have a sample of different 3-body calculations, different animations. So this is actually mean of that sample. And you see that how it goes here. And then clearly see, like, if you go to a deeper bound states, emulation becomes easier. But they all have come to one problem here is that near threshold, because there's a singularity here. So the error actually increases. This is always a problem for any, like, as soon as you have a scattering problem, a continuum problem, if you just use a matrix, calculate that, this is always the issue. There's no way around it. Okay, very quickly now, about the challenges here. So this is an extrapolation procedure. So it's going to be sensitive to noise. How to address that? This has to be addressed in collaboration with realistic calculations. So I'm going to talk about different collaborations that are ongoing right now. So with this group of people, Alex and Vijaya and others. So we're trying to explore this idea with other methods, obviously harmonic method, and later with couple cluster. So these are hidden for response functions. Okay, so very quickly. So this is from LIT. Okay, this is from our method. So these are extrapolate. So we can see like this, I mean, I'm trying to get something right near threshold, but it couldn't. The LIT is building that behavior by the analytic square root structure. Okay.
So there's, if I'm not mistaken, there's some, so this is a problem of the inversion. I actually would predict that if you take your response and you calculate its Lorentz transform just by integrating and you compare it with their Lorentz transform, it will probably look much better, right? So this problem is coming from the inversion.
From inversion or from the extrapolation from context.
Right, but then isn't there some other papers where they do the inversion in a particular way to build in that threshold?
Exactly. So this is where it's built in. So if you go to the arrow here, because the square root, they build in.
So you mean the red curve is actually better than the green ones?
Yeah. So because
I thought it was.
emulation is trying to emulate that behavior, but you know it's actually very challenging. This is not a continuous function, the derivatives.
Yeah.
Of course, like applications, because the couple class method have been making a lot of progress in the neutrino nuclear scattering. So all these formulas can be used to get emulators for the neutrino perception calculation. So the other one is really because Nambu was visiting Africa here. We are talking about this idea. It turns out in the DFT calculation, the QIPA, okay, so DFT you can get ground state, but then there's a way to access the exciting states, okay? So I mentioned that's one way to get the bound state spectrum, right? But even bound, not talking about continuum, just a bound state spectrum idea is very useful here because that will speed up their spectral calculation dramatically. So now they can do more complicated calculations than they can do before because the simple calculation are already expensive enough. Of course, if you start thinking about emulation for the other parameters, right, they can look at response function, all those things, they can emulate all those things. And I think I don't know whether he is here, so he's doing the relative state field theory or relative ERT calculations, and he's also exploring this with some very positive results. Also, the other one is Berlin basis stuff. So I'm working with these people. They're also visiting us at FRIB. So we kind of start discussing these things. So you can basically apply the Berlin basis method to calculate those training calculations. Okay, you can do it. And then this is the spectrum you get. Very clean. First of all, you have much less number of poles or eigenvalues than the full calculation. Okay, and you can see now the resonance here, this is from the exact calculation, and this is emulations here. Okay, you have a separation now between these ones, eigenvalue, and all the others. These are the branched out states. Of course, if I have bound state, then it will show up as eigenvalue 2. Okay. So we're also looking at how this kind of idea can be helpful for iterative method. We applied it to the non-Hermitian matrix argument system. Of course, you can also study the parameter emulations. The last one is kind of we just started discussing together with Alessandro. He's a student at MCU, first year undergrad actually. So we started talking about neural net. What? Second, okay. So basically that, so we have this very encouraging results from the neural net-based version and power method. You can use that whole machinery to solve those training calculations. So then you get a subspace, you can use the subspace to get excited states. So I'm not even thinking about the resonance of those things, just look at the discrete exciting states. So this is a toy model, like a single particle in one dimension, okay, with some neural net solutions. And this is the exact results. And this is from this idea that you can get qualitative reproduction of those spectrums. And of course, in the future, you can push it even further to think about resonances and all those things. And of course, parameter emulation is always associated with it. Okay, I don't have time here. Just quickly mention that this was actually in the proposal initially, the 5-year long proposal about emulating the nuclear reaction network. And Sudama was here, so we kind of start discussing and trying to explore this idea for emulating reaction networks. And it would be very useful for propagating accurate isotope measurements to the eventual elemental boundaries predictions. And for me, I'm very interested in the connection between emulation in the frequency domain and time domain. And there was a lot of discussion about time-dependent dynamics in emulations. There got to be some connections. Summary, so two types of emulated quantum continuum states. Okay, so these are status. We want to have some real energy emulation results for ND very soon. The CR papers should come out very soon. Now, there's various collaboration going on, even within STREAMLINE, and yeah, that's it.
Thank you for an excellent talk. Are there questions for Xiiln? Yeah, Elliot.
If you go back to the slides on and something like two plots, one on the left and one on the right. The one on the right, I think, uses this star as well. Can you, so it looks like using this star as well doesn't really change the real part. So if I move the blue, but then it does change the imaginary part. So the excited states and zero imaginary part.
So
that's what you want.
Yeah, so these two different setup, right? So I mentioned in the very beginning that you can put training points like on one side of the complex plane or on the both side of the complex plane. So this is for the both side of the complex plane.
Okay, this works better for
Yeah.
excited states because they're
For the excited
relevant and they're
Yeah.
on the real plane.
But for the exciting state, to do that, you can do this, but then you will screw up your continuum. You won't see the references.
Yeah.
So now if you want to see the references, you have to do that, and the first setup, and then you will see that so this is not terrible. Look at this is the number here for the real axis, and this is the imaginary. It's not that bad.
Special.
Yeah, so I think I know the answer, but to make sure I understand it correctly, I would have still asked, so you start with a Hamiltonian and it would be Hermitian if you just take a given Hamiltonian, right?
Yeah.
So the first thing you do is you make it somehow non-Hermitian by changing one parameter and making it complex.
Well,
Because you need to get something to get the complex
so
energy.
that parameter is complex energy, right? It's the complex energy solutions make it complex. But
No, but
then,
then, sorry, so if you have a Hermitian Hamiltonian.
Yeah.
Per se, it would have a real spectrum, right?
Yeah.
What do you do to get a complex eigenvalue? I thought you would already have to modify the Hamiltonian to
so
give it.
no, not modify that. So you have these. Right, at different source, different energy. So the.
That's also
This is complex.
Just
But
homogeneous.
when you calculate the Hamiltonian, right, reduce the matrix. So turns out the variational approach, actually this, I didn't say that. So there is a variational approach for solving linear equations in general. So if you follow that variational approach, we'll see that the way you compress or project your Hamiltonian matrix is actually this. So you have a complex conjugate already in the broad state, and then you have the variable here is complex conjugate.
So now you're saying you're doing explicitly a variation calculation by picking a basis, or?
Yes, so when you figure out, right, so you have these ansatz. Right, when you figure out those coefficients, right, you need to find a way, you use Gaussian projection or use a variational approach. So the variational approach will automatically force you to go to this place, that you reduce Hamiltonian matrix element, actually use a C product. Use a C product, because this is a complex conjugate twice, okay? So what it tells you is that you're actually doing analytic continuation, and analytic continuation hate doing complex conjugate once. So this is how you get a complex symmetric matrix.
Okay, so then if I may follow up, so then if I wanted to just take a Hamiltonian and put it in some basis, say oscillator.
Yeah.
That wouldn't work.
Yeah, work too. So these are actually some more results I'm showing here.
How?
Use a Thomas database.
Yeah, but then my question is how to make it non-Hermitian? If you have a
This one.
oscillator basis and Hermitian Hamiltonian.
This one.
Because
So
the
here,
I think
this
you have
is
thought
nice.
in a basis which is not, it's not like VIH VJ, it's VJ star, it's VIH, a different VJ star, because it's VJ, VI or E star.
So you pick a non-Hermitian basis.
Yes,
Okay.
So
I think.
Yeah, I'm not.
So the bases are complex first, and then
Okay.
the product is the C product.
Okay, so in that sense, it's very much like complex scaling.
Yeah.
Because
Yeah.
complex scaling achieves the same thing.
Yes, but we are not doing so we are not scaling any, we're not introducing a new main.
But there's different ways. You can do Bergen-based complex scaling. They all have the same goal of making the basis so that you can get non-Hermitian spectrum, and you're doing a different variant of that.
Yes, essentially you can say that is a many-body version of those non-Hermitian matrices, because these bases actually have all kinds of correlations, not
Also
single
different from
particle.
Bergen basis then, because Bergen basis is also a many-body version of.
Well, the Bergen base is like a direct product of single particles, right? So here is like these bases already have correlations, because there are solutions of some equations already. So, but it's you can think about it in that way. It's actually a many-body, correlated many-body basis along those non-Hermitian approach. Yeah, but it's complex.
Any other questions?
Very small one. You might have said this, but what is even and odd?
Oh, so for one dimension problem, you have parity even and parity odd.
Do you enforce that?
So you can enforce it, right? You can enforce it in the constructions. So you have parity odd, and parity even sector, they are completely coupled.
Okay.
Okay. Any other questions? No, let's thank Xiiln once again. All right, so now we will have, so I should mention lunch will be ready at 12:30, so we'll have a brief discussion. So it's an open floor, but I did want to just pull up something that was kind of interesting. I learned about it just last night, so where I can go. There's this. Yeah, I just received, I don't know, maybe some others have received a message from Elena Opera at NSF. She was mentioning this thing, the National Artificial Intelligence Research Resource Pilot. It aims to connect US researchers and educators to computational data and training resources needed to advance AI research and research that employs AI. Federal agencies are collaborating with government-supported and non-governmental partners to implement the pilot as a preparatory step towards an eventual full NAIRR implementation. And so what's basically happening is they're giving us access to resources, researcher resources. So the website is nairrpilot.org. I'll email the link to that, people. But so this just opened May 6th, so just a few days ago. Projects will be awarded for up to 12 months duration. So you can read more about the sorts of things that are available, resources from Amazon, all these different places. You can see there's some NVIDIA, OpenAI, a bunch of things here. Okay. I think that should be kind of interesting to a lot of people. All right, but that was not the only thing I wanted to talk about. So we had a second day of really nice talks. So I'm really impressed. Like I said, the first day, the DOE is not paying us enough. Yeah, but were there any other things that people wanted to talk about? Maybe especially from today's talks. There are a lot of interesting things about continuum, about variational Monte Carlo.
So before we all disappear, I want to echo Christine and thank you for organizing this wonderful symposium.
I want to add a personal statement, just like we started in 2019, we had an FRIB a School of Machine Learning. And many of the people in the audience were actually participating. And the kind of level of knowledge of basic machine learning networks was actually not very good. And many people have barely scratched the surface. When you look at the talks, which we've been having about new young folks here, just an amazing point, really. So I was really impressed by what was presented. Really.
Yeah.
Thanks to all of you.
Yeah, I have to say, my brother was kind of impressed by what you guys are all doing.
Kind of.
He always understates things, but he was impressed. All right, anything else we should talk about? Not, then thank you everybody for coming. Safe travels back home, or if you want to stay for lunch, or if you're staying for the tour at 3 o'clock, come back here at 3 o'clock. So thanks everybody for coming.
Thanks, Steve.